Yeah. Thank you so much for joining. I'd also like to thank the AuthorAID team and for our facilitator of the event, Felix, for joining us today. And I would like to start with a presentation by setting some housekeeping rules. They are not big rules, but some general things that we need to consider while we go ahead with the webinar. So today, Felix Emika is, who is also a research and data scientist, will be the host of the webinar. We will have total of 90 minutes for the webinar, 60 minutes for the lecture session, and rest of the minutes for the question and answer. So we have like half an hour for the question and answer. Please utilize this space for learning as much as we possibly can. So looking forward to that. So the session is on Beyond the Numbers, Correcting Myths and Misconceptions in Statistics. I'm really excited about it, and I hope all of us are. So general housekeeping rules are, okay. So like I said earlier, we are recording the session and your participation will indicate consent for recording the session. The other one is closed captions are available. You can click on the CC button below. You can see it somewhere down. Let us know if you cannot access it. We can help you. So if you have any technical issues, please let us know via the chat function, or you can directly email at asta.subedi@inapps.info. And I would also like to request everybody to mute yourself when you are not talking. It will reduce the background noise and it will be really fun. And also raise your hand in the participants panel if you would like to ask a question during the Q&A. Those questions and comments can also be submitted at any time in the chat. So please, you can utilize the chat box and also raise your hand, and we will be giving the platform for you to share. I would, before handing it over to Felix, I'd like to introduce him. So you can see Felix there in your screen. So who is he? He is an accomplished research, analytics, and data science professional with demonstrated ability to develop and implement data-driven solutions in the urban and health sector, with over 10 years of experience in teaching and leading epidemiological, biostatistical, and data science projects, from descriptive to predictive analytics. He's also a trained research scientist, scientific writer, and epidemiologist in his day-to-day duties at the Center for Health and Development, a center that evolved from several years of international research collaborations between the University of Port Harcourt and Dalai Lama School of Public Health at the University of Toronto, Canada, and most recently the University of Ottawa, Canada. CSD aims to develop human and organizational capacity for health-related research and quality healthcare provision in the Niger Delta region of Nigeria, built on sustainable local structure and international collaborations. He is a convener of AuthorAID Data Science Hub, one of the guest facilitators for AuthorAID online course, and a biostatistician for the AuthorAID online journal club's projects in apps. Also, he advises on a potential curriculum for statistical data analysis online courses. So a lot to learn from him. I'd like to hand this over to Felix.
Okay, thank you, Asta, for that powerful introduction. Thank you, Andy, and the INAPS team for the honor to have me as a guest in this webinar. I'm happy to be here, and thank you, everyone, for showing up. And I know we're going to be able to have a lot of take-homes today. Thank you. So I will share my screen now so we can begin. So let me sit here. I wanted them to see my face because here it's not clear. So, good. I hope you can see my slide. Sorry. Let me screenshot. I hope you can see it.
Yes.
Yes.
Okay, all right, thank you. So we will be looking at beyond the numbers, correcting myths and misconceptions in statistics. So how do we begin? By this wonderful photo that I always present that says, without data, you are just another person with an opinion. In other words, data, it's everything. When you're able to make decisions with data, most of the time, those decisions are valid and they are most often representative. So as statisticians, as data scientists, we've been learned in the philosophy of using data to make decisions, not just our personal opinion. Now, what is statistics? I'm using the definition of Tolkien because he's one of the renowned statisticians, one of the fathers of statistics, and he defined data analysis in a very beautiful way that I love so much. He says, one, ways of planning the gathering of data to make its analysis easier. Because a lot of times we're often carried away by the analysis and we pay less attention in how this data is collected. The quality of the data that is analyzed has a strong relationship with the way the planning of that research is done, how that data is collected, how that data is cleaned, and how accurate that data is. These characteristics play a role in the quality of the analysis and the result that you are going to get. Like I often say to my students, to consult a statistician when the analysis is completed is like telling the statistician to tell you what the research died off. Because if you are having an issue after your data analysis is completed, it means you are consulting the statistician at a very wrong time. Your statistician should be brought in at the beginning of the project, before you even begin to gather this data. Because one of the things I do for students is to ensure that the data tool you have designed or the questionnaire you have designed is in line with the study objective for that research you want to do. Because if you design this data tool and you take it to the field to collect this data and you return, and you now find out that one or two of the objective is not representative in the data you've collected, then there's a good chance you may have to go back to the field to recollect this data, and that can be quite expensive. So these are part of the benefits that you get when you consult a statistician. And one of the things he mentioned too were techniques in interpreting the results of such procedure, because you have to also have this skill, which is one of the things we'll be talking about here. It's not enough to be able to analyze the data. It is also a good thing to be able to tell appropriately and accurately what the analysis result is saying. And finally, the statistical tool, the machinery, the algorithm, everything that comes into play in analyzing that data is what Thoki packaged together to give us as the process in terms of what statistics could be. So there are two primary branches, the descriptive and the inferential statistics. So we will just look at examples of it. What is the descriptive? Descriptive is something like this. Okay, this is one of the papers that I authored at my university, Durban University of Technology, where we looked at knowledge, practices, and attitude of COVID-19. That was 2020, 2021. So Table 1 just looks at the demographics. So this is an example of a descriptive. You don't make any inferences, you just describe the data. In this case, we describe the gender, male, female, how many males, how many females, what is their age range, what is their marital status. So this is what descriptive statistics is all about. You just describe the frequency and the percentage of the data the way it is. You don't need to make any inferences. Another example could be this. Sometimes if you don't want to represent it in a table, you can represent it in a chart, like a pie chart we have here. Just describing the data, that's all. No form of inferences. But that could be slightly different when you're talking about the inferential statistics, because the inferential statistics, you're going to be stating a hypothesis and you're going to be making some inferences and you're going to be doing some comparison between two variables. For example, in this case, the example table I have, you would see that at one side, it has self-reported occurrence of tinnitus ringing in the ear. This other side, you're looking at the outcome, which is the noise-induced hearing loss. So you're trying to see whether those that says they have constant recurrence of ringing in their ears will most likely have noise-induced hearing loss. The tinnitus you have, yes, they have it. No, they don't have it. The noise-induced hearing loss, yes, they have it. No, they don't have it. If you look at the percentages, you would be able to tell that those that have tinnitus, 72% of them have noise-induced hearing loss, while those that don't have tinnitus, 27% of them do not have. So we can say from this data that we are seeing a more prevalence of noise-induced hearing loss among those that have ringing in the ear. Is there an association? Is there an evidence to show that what I just said now is true? Because we're comparing percentages, 72.94 against 27.06, which you have here, we would be using the chi-square, which is the test of significance when you're comparing percentages. So from the chi-square value, which is 70.38, and the p-value, which is less than 0.05, we can categorically say that those that have ringing in the ear will have a higher prevalence or a higher percentage for noise-induced hearing loss. So this is an example of inferential statistics. We are making inferences. Apart from the chi-square, you can also do bivariate logistic regression, which is the odds ratio here. So the chi-square has shown us that those that have ringing in the ear have more prevalence, more percentage of having noise-induced hearing loss. That is what the chi-square is telling us. But the odds ratio tells us something different. The 14.96 here, which is the odds ratio for this same association, is telling us that those that have ringing in the ear are 14.96 times more likely to have noise-induced hearing loss. So this is what inferential statistics is all about, where you make inferences. So I'm making an inference here to show that there is a significant association between tinnitus and noise-induced hearing loss. Another example is this, where you're having an association between how long they play the musical instrument and if they have noise-induced hearing loss. And from this data, you can see that those that play more frequently has more noise-induced hearing loss, 61.18%, over the others that play once or sparingly. But interestingly, you can see that the test of significance here is different. What we use there is actually a Fisher's exact, not a chi-square. Why did we use a Fisher's exact P? Because in the association, we have values that are less than 1. Anytime you are doing an inferential statistics, an association of an independent variable, in this case, frequency of playing music instrument, and the outcome variable, in this case, the noise-induced hearing loss. And in your association, you have values that are less than 5, you would be using the Fisher's exact P and not the chi-square and the p-value. All right? Because the Fisher's exact P, it's a test of significance that are just for smaller numbers. So apart from this form of association in inferential statistics, you can even have the adjusted odds ratios, meaning when you have done the crude odds ratios and you've seen that there's a significant difference in the association, you can test for confounders, which we have done here, between the different variables and the outcome, which is level of preventive practices, and they are interpreted the same way. They are interpreted the same way. Like for these one, the first one is showing us orders, male and female. And from the odds here, you can see that male is 9.815, female is 1.692. So what does that tell us? That simply tells us that the male gender, they are 9.815 times more likely to have good and adequate level of preventive practices of COVID-19 compared to the female gender. So they are interpreted the same way. So these are what the inferential statistics look like. Even the Pearson's correlational coefficient is an inferential statistics, because it's telling you if one continuous variable is increasing, is the other one increasing? Like we can see here, as the PM10 is increasing, the PM2.5 is also increasing. These are variables for measuring air, air quality. So from the coefficient, which is 0.23, which is positive, we can say, although this is weak, but we can still say that as one variable is increasing, the PM10, the PM2.5 is also increasing. So these are it for inferential statistics. There would be no inferential statistics if you are not doing an association of two variables. So I wanted to show us some of the statistical tools we can use for basic statistics and also for data science too, depending on what you want to use. I use almost all of them, so, and they all have almost the same result. I don't have a preference. Depending on what data analysis I'm doing, that is what we inform what data analysis tool that I'm going to use. But I always recommend students to source for open source statistical software like Arrow. Arrow is open source, it's free. EpiInfo is open source, it's also free. All right, Excel can also run some basic statistical analysis. All right, so what are the roles of statistics in making decisions before we go to the myths and misconceptions? One of it is data-driven decisions. I mean, we can see Netflix, for example, they use the data of subscribers to know what sort of movies to recommend to them. In data science, we call that recommendation system. It's an aspect of machine learning where the data learns the habit of people and it's able to recommend the movies based on the nature of the kind of movies that a larger population of people have seen. It uses that to recommend to others. And sometimes you may get thrilled and say, oh, this is the kind of movie that I would like. How did the system know that I want to watch this sort of movies? It's recommendation system. Data helps drive those kind of decisions. The other one is risk assessment. A lot of companies use statistical data like your age, your health, your history to determine if they are going to give you loan or not, especially the insurance company. The other one is business planning and forecasting. You've heard of predictive analysis. Businesses use their retail data to predict what kind of goods sell in a particular season. Like we have the Christmas season coming up. Good businesses will use the data they have gathered over the years, analyze it, and be able to tell which products sell more during the festive season. And that way they will have enough stock and not have issues with low stock. The other one can be quality testing, called the Six Sigma. A lot of companies use the Six Sigma, especially the Motorola that found it. They use it to actually test for the quality and the durability of the car parts they are manufacturing. And it can also help them check what parts have defect, and they are able to figure out what is causing the defect and correct it. The other one is policy making. Especially in the COVID-19, we saw how governments of many countries use data to actually make policies that favor them during the pandemic. And the final one is scientific research, clinical trial. A lot of them were done. And because of that, we had a lot of information that also helped in the development of COVID-19 vaccines and testing their efficacy rate and evaluating their safety and all those sort of things. All right, so that is a background that I really needed to share so that we will all be in the same picture. Now we will dive into the myths in statistics and see, how we can actually correct those. The first myth is correlation implies causation. Because sometimes people feel when they do a correlation, it simply means the independent variable is the cause of the dependent variable. I will give a very good example based on the picture that you see here. This is a scattered plot, which is a correlation chart. As you can see, we have years of music experience, meaning how long they have been playing the musical instruments. Then we have the HHQT, which is the hearing held quick test. It's actually some numbers that shows that the higher the number, the severity of the hearing problem. While the lower the number, the mild of the hearing problem or no hearing problem at all. So from this Pearson's correlational coefficient, what you can see based on the line, as the years of music experience is increasing, the severity of their hearing loss is also increasing. That is what this correlation is showing. But this correlation only tells us an association between the number of years they play and how that could influence their hearing loss. But it doesn't mean that because they have played for long, it is their years of experience that is causing their hearing loss. The hearing loss is probably caused by the hearing loss is probably caused by their exposure to loud sound. That is what might be the cause of the hearing loss, not necessarily because they have been playing for a long time. The reason why you do a correlation is to see whether there is an association. So from this correlation, I can tell that someone that plays for long, due to their excessive exposure to the cause, which is loud sound, they would most likely have severity in their hearing loss. Not because they are praying for long, that's why they have hearing loss. So you see, correlation does not imply causation. Because I've seen students interpret it in such a way, it feels like the independent variable is the cause of the outcome. If you want to do a study where the independent variable implies or infers the causation, then you will be looking at things like the randomized control trial. You'll be looking at things like the randomized control trial, because in the randomized control trial, you as the researcher, you are responsible for the intervention. For example, you want to test how good a drug is among some cancer patients, and you have the intervention drug, you also have a placebo. You administer that drug to some patients you have randomly selected, and you follow them over time in a longitudinal way to see whether they will have some respite or some healing property from that drug over time. And if that happens, because you are responsible for that intervention drug, you are following them over time, you're monitoring their progress, you can for sure say the intervention of that drug is responsible for the outcome you are seeing, because you are responsible for that exposure, so you can control it. But in a case of like a cross-sectional study where the exposure is in the environment, imagine people going to a religious house, going to a concert, you were not responsible for the exposure. The loud sound is there, so you cannot truly make an inference because you didn't have a controlled environment where you can test that exposure. Another example is the cohort study. In a cohort study, like one of the research that I did in my bachelor's, I had 42 white rats, and I exposed them to a plant extract, Phyllanthus amaris. I exposed some to lethal dose. I exposed some to minimal dose. I exposed some to water. And I followed the rats over time. And after 1 week, 1 month, the rest, I will sacrifice them and do some histopathological analysis of their liver. That way, I was able to see that the high dose extract of that plant can actually cause some negative histopathological changes in the liver of the rats. That's a cohort study. You expose them to the condition or whatever you want to use for the exposure. You follow the organisms, the humans over time, and see whether they will develop the outcome you're interested in. Whenever the outcome, suffices, you can say for sure that that exposure is responsible for the outcome. But in a correlation, like a Pearson's correlation or a Spearman's correlation, or even a correlation using the chi-square, they don't imply causation, because whatever they were exposed to was in the environment. You were not responsible for that, so you can't infer causation. So that is the first myth that I have corrected. So we would look at the second myth. Statistics does not always tell the truth. Now, why I had to bring this, because I have had issues with this, in my career. Sometimes you would analyze the data and you will share that data, and the clients will come back to you and say, oh, this variable is supposed to be 20, but I'm seeing 15. Or this is supposed to be this, and I'm seeing this. And I always tell them that the data does not lie. And in 100% of the time, I am correct, because the data analysis, the statistical analysis will always generate the output from the data that you have. So if your data is analyzed and the prevalence of whatever outcome you're interested in shows 20%, and you say, oh, no, that number, something is wrong. There's a mistake somewhere. It's supposed to be 15%. You have to go back to your data, because your data, your statistical analysis will always infer your data. So statistics does not lie. What could be the cause may be how the data is interpreted, or the data itself, which probably was not collected properly. Which is why, as a data analyst, I always encourage statisticians, when you collect data, please spend some time cleaning up the data. Do your homework well, which is the data cleaning. And do these side by side with the client, so that they see the data that has been given to you. An effective data cleaning process would most likely brings out the real outcome of that data in the data analysis, unlike a data that, you are just given a data and you begin to analyze it. Sometimes you can have an outlier. Sometimes you can have characters that are not supposed to be in that data, and they would not be analyzed, and the client will feel that you didn't analyze, that the statistical analysis that is given to them is not correct. It's all from the data. So once the data collection is done right, the collation is done right, the cleaning is done right, when you analyze the data, it would most likely show you the true context in that data, because the data analysis only provides an output of what is in the data. So that is the second myth. So what is the third myth? Bigger sample sizes are always better. Well, this is not always the case, because in every research that you do, there's usually what they call sample size determination. When you're carrying out a research, you don't just assume the number you want to use. You don't just say, oh, I want to use 100 persons. I want to use 200 participants. I want to use 300. No, you don't guesstimate sample sizes. You calculate them systematically. All right. And I provided some examples. This is an example of a formula you use for a cross-sectional study. This is the way it looks. The N is the minimum sample. The Z is a constant, which is 1.96, corresponding to the 95% confidence interval. You have to look for the P. So if you're doing a study on the prevalence of preeclampsia, for example, you have to look for a previous study that they did in your region and get the prevalence of preeclampsia. That is what the P would be. Then the Q is the 1 minus the P. The E is the tolerable error or level of precision, which is a constant, 0.05. So you put all these numbers in the formula. Whatever number you get, that's your minimum sample size. Then you can do 10% non-response, add a 10% of that number to accommodate for non-response for a cross-sectional studies, but for a randomized control trial, we'll call it attrition. All right, so this is usually the formula for a cross-sectional study. We also have formulas for comparative study, where you're comparing the percentages of two, populations in a cross-sectional study. This is what the formula looks like. The Z alpha is a constant, 1.96. The Z beta is a constant, 0.84. All right. You will have to look for your P1 or your P2, depending on the prevalence for the first population and the prevalence of the second population. So you put all these in this formula and you calculate your minimum sample size. This is another example of a sample size determination formula, but this time for studies where you're looking for outcome in means, not proportion. For example, if you want to look at a study that has to do with the average systolic blood pressure in an environment, then you would be using this formula. All right, because you now have to look for a previous study that has an average systolic pressure in that environment, and that will be, then you would look for the standard deviation of that mean of that previous study. That is what will be in your S and a square. So these are 3 examples of sample size determination formulas to show you that your sample is calculated. I completely agree that larger sample can reduce tolerable error. Yes, that is why you're asked to determine your sample size. Because when you use a formula to determine your sample size, whatever sample size you get already has the tolerable error adjusted to it. Like I showed you the first one, the E square adjusts for tolerable error, which is also called the level of precision. So if you calculate the sample size and you get 200, that 200 you have gotten is a representative of the population of that sample because you calculated it systematically. All right. So don't be carried away with how big the sample, because I've seen students after they follow this formula and calculate their sample size and they have like 150 and they are worried and say, oh, this is too small. Can I make it 300? Can I make it 400? No problem. You can make it 300, you can make it 400. The bigger, the better. But if you had calculated a sample size of 100 and you decide to use 100, that's not a problem, because that is what you systematically calculated is fine. But if you feel you want to increase the size and 200, no problem. Your sample size determination calculates minimum sample. It calculates the number or the size you cannot go below. But if you want to increase above your minimum sample, it is welcome. So the bigger sample size is good, but it should not be at your discretion. You don't make that decision. Your sample size determination formula makes that decision. All right? And also, I also want you to appreciate the fact that there are some studies where the larger sample size does not count. Like for a qualitative study, you don't require large sample sizes, because a qualitative study uses what they call data saturation. Like for one of my, for my PhD, the qualitative aspect, I'm using 15 persons. And 15 persons, I was able to achieve data saturation. Data saturation is that point where your participants begin to tell you the same thing all over again. You know that you've got into a state of data saturation. So in those kind of studies where you don't use a probability sample, meaning you use a convenient sample, size does not matter. So for a qualitative sample, will you begin to talk of bigger sample size? You know, not at all. So what is most important when it comes to the sizes is not how big that size is, but how you are selecting that sample. Because you have to ensure that when you have calculated your sample size and you have 100, how you select that 100 is very important, because that 100 has to be a representation of the entire population. So that is why for quantitative study, we always recommend probability sampling, random sampling, stratified sampling, cluster sampling. All right? We try to encourage researchers to avoid non-probability sampling, like convenient sampling. You do that for qualitative, but not for quantitative. All right? So the sampling helps you to balance up your sample so that you don't pick one group more over the other, and that way the entire population is not a representative of your sample. So what is the fourth myth here? All variables follow normal distribution. You know, when you collect your data, we encourage, like I said, the probability sampling, meaning that you can use random sampling, systematic sampling, cluster sampling, and the rest of them, so that that sample is a representation of the population. But it is not all variables that can be normally distributed, even if you collect that data in this way. So if you collect your data using the probability sample, yes, we encourage you to do the parametric method of data analysis. So if you have data for human height, human weight, IQ score, all these kind of data, they have a normal distribution in the sense that all these sort of data, they have a normal distribution in the sense that you would even notice that naturally. For example, human height. If you collect the data of human height, you'll find out that majority of them will fall on the average. You will just have very few that are on the extreme end, most tall and most short. Most of them will be average. The same thing with weight. Most people would be on the average weight. The same thing with IQ score, intelligence. intelligence quota. When you give an exam, you find out that majority of them will fall in the average. Very few students will have exceptional A, an exceptional F. So you see, these sort of variables, in their nature, they are normally distributed. But when you want to collect them, yes, we recommend probability sampling. And when you collect this sort of data, we encourage you to use parametric method of data analysis. So meaning that if you're going to be comparing means, like if you're comparing two means, we encourage you to use the student t-test. If you're going to be comparing 3 or more means for this kind of data, checking for differences in 3 or more means, we encourage you to use the ANOVA, analysis of variance, also called the F statistics. That's parametric method of data analysis. But there are some data that don't follow normal distribution. For example, population height. You may have more population in one region in the urban compared to the rural. It may not be balanced. So there's skewness in the way people live. There's also skewness in income. You have the extreme people that are so rich, and you have the extreme people that are so poor. So you find out that the people that are the average, they are very few. So income data is already skewed. So if you collect the data in your questionnaire like income, we encourage you to use the non-parametric. The non-parametric method of data analysis adjusts for this skewness. So if you're going to be checking for the central tendency, meaning the average, for this sort of data that don't follow normal distribution, if you're comparing the medians, which is the measure of central tendency, you'll be using medians. So if you're comparing 2 medians, you'll be using the Mann-Whitney. If you're comparing 3 or more medians, you'll be using the Kruskal-Wallis. All right. So you have to pay attention that it's not all continuous data you collect that you're going to be doing means for, because I see that almost all the variables you're doing means and standard deviation for them. Some of the data like income does not follow normal distribution, so you can't do mean for it. You have to do median. So if you're doing association using medians, for 2 medians, Mann-Whitney, 3 or more medians, Kruskal-Wallis. But for data that follow normal distributions, fine. For comparing 2 means, student t-test, 3 or more means, the analysis of variance. Okay? But you can validate the distribution of that data to tell whether it's normally distributed or not. You can use what they call the Shapiro-Wilk normality test. We have that in Arrow. We have that in SPSS. So you put that continuous data in the Shapiro-Wilk and you run the data analysis. If it gives you a p-value that is less than or equal to 0.05, the interpretation is that the data significantly deviates from normality. So as long as you run the Shapiro-Wilk, it will generate a p-value. Once that p-value is significant, the interpretation is that the data significantly deviates from a normal distribution. So if the p-value is significant, you're not going to be using parametric method of data analysis. You're going to be using non-parametric, meaning you're going to be working with your median. But if your p-value is greater than 0.05, it means that data is normal. So you can use parametric, meaning you're going to be working with means. So that is the 4th myth. All variables follow normal distribution. So what is the 5th myth? No hypothesis significant testing provides definitive answers. And I'm going to explain this. Initially, at the beginning of this webinar, I showed us an inferential statistics. And that inferential statistics, I was looking at tinnitus and noise-induced hearing loss. Tinnitus and noise-induced hearing loss. And the association showed that those that have tinnitus will most likely have noise-induced hearing loss. That is what the odds tells you. It is odds. That means it is a probability. But before I commenced on that study, I had a null hypothesis. And what was the null hypothesis? The null hypothesis was that there is no significant association between tinnitus and noise-induced hearing loss. There's no difference between having tinnitus and noise-induced hearing loss, meaning whether you have tinnitus or not, it does not impact on whether you would have noise-induced hearing loss. That was my null hypothesis before I ventured into that research. After that research, I collected my data, I analyzed that data, and that is what I found. I found out that those that have tinnitus will most likely have noise-induced hearing loss based on the chi-square and based on the p-value, which was statistically significant. So what did I do? I rejected my null hypothesis that says there was no difference or significant association between tinnitus and noise-induced hearing loss. And I accepted my alternate hypothesis that says there is a significant difference between the tinnitus and noise-induced hearing loss. But does the null hypothesis, which I have rejected, which says there's no significance, and I accepted my alternate hypothesis, does the null hypothesis infer that all those that have tinnitus will have noise-induced hearing loss? You see where the problem is. So even if I reject my null hypothesis, or I accept my null hypothesis, this rejection and acceptance does not provide definitive answers. Even if someone have tinnitus, there are a lot of factors that could even promote the noise-induced hearing loss. It is not just having the ringing in the ears. Let me give another example. You have a drug. You're trying that drug, and you want to see how effective that drug is. For example, let's say it is a cancer drug. You state your null hypothesis. There is no significant difference between the utilization of this drug and the cure of cancer. And you start the clinical trial, and you started giving the person the drug. And at the end of the day, you notice that as the participant is taking the drug, it is helping with the cancer. By the time you finish that trial, for that particular study, you found out that there was a significant difference between taking the drug and the participant having relief of the cancer. Maybe they were at stage 4 before, they are now in stage 1, meaning there was a good progression. So in other words, you would reject your null hypothesis that says there's no significant difference. So you've accepted your null hypothesis that says, yes, a difference was seen. The new drug works for cancer. But you have to remember that that experiment you have done is just in one setting. The fact that you rejected your null hypothesis does not provide a definitive answer in totality that that drug will work in all phases, in all ramifications. Meaning you have tested that drug in your region, probably in the US. That drug has to be tested in Britain. It has to be tested in Nigeria. It has to be tested in Kenya. It has to be tested in other countries. As I speak to you right now, there's a clinical trial that I'm part of the team. That clinical trial, it's actually testing the effectiveness of an intravenous ferrous drug. What is the condition we are looking at? Women, postpartum anemia, women that have postpartum anemia, meaning women that have anemia after they give birth. In Nigeria, when women give birth and they have anemia, they are prescribed tablets. They take these iron tablets for almost six weeks, and with the hope that that tablets will build up their blood over time. But there's this new drug that has been tested in a different country. It shows to be effective. But we are now testing that drug in Nigeria before it can be sold here. We are doing a clinical trial of that drug. It's an IV drug for postpartum women. You infuse 200 ml of that drug, and the drug has the potential to build the blood cells. So they don't have to be taking tablets every day, just one infusion, and that is it. So the fact that the first setting showed a significance, that is not a definitive answer. There has to be other evidences. That experiment has to be replicated in other settings. So just rejecting your null hypothesis in one study is not a definitive answer that that drug is effective. You know, so that is a myth, because sometimes we don't put in cognizance that whatever you have done is just in one setting. You have to replicate that study to actually test the effectiveness in other regions. That is why systematic review is one of the high level of evidence after randomized control trial. Because in systematic review, you now have to bring systematic evidence of different studies that have been done in different settings to bring them together and prove a narrative. But apart from the systematic review, there is even a higher evidence above a systematic review, which is the umbrella review. The umbrella review is the review of systematic reviews. That's a higher evidence now. So that's the fifth myth. So we are going to be taking the last myth, the final myth before question and answer. The final myth: you can compare two groups with different sample sizes differently. You can compare two groups with different sample sizes differently. As statisticians, we try as much as possible to ensure that if we're doing a comparative study, both groups are similar. It is not good to do a study and one group is 100, the other group is 500. Sometimes it can create some bias in the result. That is why we'll always recommend using stratified sampling if you think you're going to have this sort of bias. For example, you want to do a study to look at a clinical difference between vaginal delivery and cesarean section. For example, in my setting, we will have more vaginal delivery than cesarean section delivery. So if you decide to collect the data from the records randomly, you just do simple random sampling, you will find out that when you finish collecting that data, you will have more participants that have had cesarean section delivery than those that have had vaginal delivery. By the time you're doing the comparative study, you may have 500 vaginal delivery and just 100 or 150 or at most 200 cesarean section. And that will create some bias because one sample is higher than the other. So that is why in this sort of research, we encourage stratified sampling. In a stratified sampling, what do? You stratify the group into strata. For example, in that environment, you have those that have delivered in cesarean section, those that have delivered in vaginal delivery. You share them into two. CS, you put them one side. Vaginal delivery, you put them one side. You randomly pick, using simple random, to pick the number you need from the cesarean section, the number you need from the vaginal delivery. That way you most likely have equal sample. But when you want to do simple random sampling from this sort of population, you will have a bias, one group having more number than the other. Another example is you want to do a study. Let's say you want to do a study on prevalence of malaria amongst military personnel, and you go to a military barrack to collect your sample. Trust me, for every 10, 15 males you collect a sample, you will have one female. By the time you finish collecting that sample, you'll find out that you may have like 300 male military personnel and 20 or 30 female personnel. Because we have more men in the military, the army especially, than the women. So you will have that skewness in the number. How do you want to do, a comparative study with that to see whether the prevalence of malaria is higher in one group over the other, in the gender, in the military personnel? Of course, there will be bias, because whatever analysis you do, it will favor the males more because they have the numbers. So in this scenario, you do stratified sampling. You bring all the male military personnel to one side. You bring all the female military personnel on another side. You randomly pick the number you need from the male. You randomly pick the number you need from the female. That way, you will most likely have equal representation of these two groups. So you're able to correct the bias of having one group more than the other. So it can be corrected. Yes, I know in percentages it can help. Like in the example that I give here, the group 1 is 12, the group 2 is 28. So if you do the percentages, it can adjust for the difference in the numbers. But you can actually control the difference in this number before you even progress in the data analysis. So you can actually have maybe not completely equal numbers, but you can have the sampling method help you in ensuring that you have almost equal representation of the two groups that you would be comparing. I think this is the final myth I would be looking at, so that we will have time for discussion. Thank you very much.
Thank you so much for the session, Felix. We have a lot of hands here. I'd like to take the question from Ifoma.
Hello, everybody. Good evening. I'm Ifoma Ekenna from Nigeria. So the question I want to ask, this is his topic is an interesting one. Thank you so much, the facilitator, Dr. Emeka. Thank you so much. So the question I want to, yes, he talked about stratified sampling. I've done a lot of analysis and I've had this issue. And most times you want to say, oh, these people are doing this. Meanwhile, the data has already been biased from the onset. So you talked of stratified sampling. You said you pick from one side, you pick from the other side. Is there an automatic way of doing it using SPSS? Or should it be done manually? How can somebody do this stratified sampling, please?
Yeah, this stratified sampling is not done by SPSS. It's actually done manually, and it's easy to do. But first, you have to have your participants. Because in every study you do, you should have like a list of the participants. And that list of the participants serves as your sampling frame. So let's say now, the example I gave, you want to look at some factors, that may be associated with vaginal delivery and cesarean section. Of course, you already know the participants. So for those that said that they had delivery using cesarean section, you have their names already. Maybe 1 to 100, you have their names. Those that says vaginal delivery, you also have their names. And you have done your sample size determination, and your sample size determination for comparative study says that you need 30% for each group. So what you do, since you have a list of the group 1 cesarean section, you have a list of group 2 vaginal delivery. You can now use simple random sampling. You go to the first group, you randomly pick. So you write the names in a piece of paper, put it in a bowl, shake it. You randomly pick 30 from the CS bowl. Then you randomly pick another 30 from the vaginal delivery bowl. So that way you have equal representation. But if you go into the pool and sample 60 people, and at the end of the day, you now separate them between CS and vagina, trust me, you may have more, vagina than CS, Yeah, so that is how you do it. It's actually done manually, but for you to be able to do that, you probably would have a list of the participants that meets the criteria for your selection.
Okay, so that also means that my sample size at the beginning has to be more, or at the time I'm doing the stratified sampling, I should be having my sample size already in mind. That is, usually what we'll do is after calculating sample size, we'll go and start getting our data. At the end of the day, you may have 60 participants. So what I'm understanding from this stratified sampling is you then separate them. Or is it that when you are in the field, you are already picking them using that stratified sampling in your mind?
No, because when it comes to stratified sampling, it's different from simple random sampling. Simple random sampling, you just pick. And at the end of the day, you figure out who is CS and who is vagina.
Yes.
But this one, you consciously know the group that is vagina, and you consciously know the group that is CS.
Okay.
From the pool of the CS, you pick the number you need. From the pool of the vagina, you pick the number you need. That way, you have equal representation of two groups.
Thank you.
Unlike the one you just go into the pool and just pick, and at the end of the day, you figure out how many is CS and how many is vagina.
Thank you. Thank you very much.
Too. Thank you too.
Now we'll take the next question. It is of the Ibrahim. Ibrahim, are you here with us?
Yes. Can you hear me?
Yes, we can hear you.
Yeah. Thank you, Dr. Felix, for this wonderful presentation, as always. Thank you so much for educating us. My question is based on the mix 6 about the different sample size. So I'm a bit confused here with that. For example, you have a situation where you expose animals like the way you did during your undergrad with the rats. So let's say for the control, not the exposed ones, that is the water one. Let's say the drugs, you dissolve them in some other like solvents before you add it to water and give it to the animals, to the rats. So you have like two controls. You have the solvent control and the water control, for example. So at the end, when you start the analysis, you see there is no difference between the two controls, the water and the solvents.
Yes.
So you decided to combine the two controls together to do the analysis instead of having two controls, since there are not any statistically significant between them. So you decided to combine them together and do the analysis. Will that also affect the analysis at the end, because you combine the two controls, which will make the control now to be double in the sample size compared to the exposed ones? That is my question.
Okay, thank you very much, Ibrahim. That's a very, very good question, which we have debated a lot. So we try as methodologists, we try as much as possible to encourage students to use equal sample sizes. We try as much as possible to do that. But there are some instances where you would not be able to do that, like in this scenario you have mentioned. So the ratio that is usually recommended is 1:2, meaning your intervention group has to be 1, then your control group has to be 2. So meaning if your intervention group is 100, you are allowed to use a control group of 200, meaning 1:2. So in your own case now, yes, you can actually do 1:2, but the control has to be larger than the intervention group. So it's allowed. It's not going to affect the result at all. But when you begin to increase that control, 1:3, 1:4, then it's the bias will come in, but 1:2 is very safe, very, very safe. Yes.
Yeah, that's
for
very
yes, for a comparative study. But the 1:2, it is the intervention group that is the 1. The control group is the 2. Is the control group you increase, not the intervention group.
Yeah.
Yeah.
Yeah. So this is very informative. Thank you very much. So at least this will not affect it because now the control group is double. That is
the intervention group. Yes, it will not affect it in any way. Yes.
Thank you so much, Felix.
Thank you too. Yeah.
Now I'd like to ask Moses to take it over. Are you here?
Yes, thank you. Thank you so much, Mr. Felix, for the presentation. It was very informative. We appreciate. I have three questions, actually. My very first question is about the comparison of different means at inferential statistics. You talked about ANOVA tests. I would like to understand the difference between one-way on ANOVA and two-way ANOVA. And also, I would like you to throw more light on what I hear, the post hoc tests, and if you can give some examples. And then I also appreciate, my second question is about the rats, the experiment you did. You talked about having 3 sets, groups of rats. One was given water, another one was a control, another one was a lower concentration, another one was a high concentration, another higher dose. I would like to know how did you, what was your outcome? What did you observe as the outcome? And how did you do inferential statistics? How do you associate? How did you know? Did you use odds ratios? Which test did you use? And then my very last question is about just the definition. I always get confusion when I hear effect size, and it really disturbs me. I would just request for those responses. Thank you so much. This was very, very informative.
All right. Thank you very much. So I'll take your questions. I noted them. The difference in the comparison when it comes to means. Like I mentioned, if you're going to be using means, ensure that you're using your data is normally distributed. So meaning that the way you selected your sample, you follow the systematic process in selecting the sample. So that will most likely have your data in a normally distributed way. And also you can use the Shapiro-Wilk normality test to actually determine that your data is normally distributed before you can apply the parametric, which is using the mean. So if you're comparing 2 means, you use what they call the student t-test. But the student t-test can be independent and paired. All right. Now, independent means that the mean is from 2 different groups in terms of 2 different values. Let me use that word. Group may be confusing. 2 different values. For example, you want to look at mean age between male and female. Male is a different value from female, but both of them are under the umbrella gender. You see, that's why I don't want to use group so that it doesn't confuse, someone. So 2 different values. So if you're looking at mean age in male and female, then you're going to be using the independent t-test because these are 2 different values you're checking the means for. But let's say you come into an environment and you notice that, or you did a needs assessment in a community and you notice that the children are malnourished. You take a pre-test of their weight, meaning, you take a pre-weight, you take their weight because you want to carry out an intervention, but before the intervention, you take their weight first. You carried out the intervention by speaking to the mothers, educating them on how to feed the children. You provided some meals and all that. After 6 months, you came back to the community and took their weight again post, meaning you took their weight before the intervention and you took their weight after the intervention. Both the pre-weight and the post-weight is from the same population, but you want to check the difference in the 2 weights from the same population. all right? The same children. So in that case, you use what they call the paired t-test, not the independent t-test now, because it's the same population pre and post. Now, if you're comparing three means, you use what they call the ANOVA, analysis of variance, also called the F-test. But the analysis of variance can be one-way and two-way. What is the difference? In one-way analysis of variance, let's assume that you have educational level. I'm trying to use simple things that we can appreciate. Let's say we have educational level, and that educational level, you have primary, secondary, tertiary. And you want to look at the mean age in primary, secondary, and tertiary of the population. That's already three categories, three mean categories: mean for primary, mean for secondary, mean for tertiary. That's three. So that qualifies as ANOVA. But this is a one-way ANOVA. A two-way ANOVA, you have to bring in a third variable. So let's assume that that third variable you are now bringing maybe educational level, maybe like the severity of their hearing loss. So the severity of their hearing loss is mild, moderate, and severe. So you want to see the mean age in the different educational level and whether the different educational level is responsible for the noise-induced hearing loss severity. That's two-way ANOVA.
Okay.
But the one-way, two variable at a time. The two-way, three variables at a time. Most times we do one way. It's rare to see studies where two ways is done unless it's really, really necessary. Now, what about post hoc? Post hoc simply means after you have done the ANOVA. So let's assume that you looked at the primary, the secondary, and the tertiary education. You looked at the mean age for primary, mean age for secondary, mean age for tertiary, and you have an ANOVA. And the ANOVA had a significant P because you only do post hoc when the ANOVA is statistically significant. If the ANOVA is not statistically significant, there's no need for post hoc. So you have a significant, so this comparative analysis is showing that those that have tertiary education have a significantly higher age. Of course, that's true. You know, those that have tertiary education have a significant higher age, mean age, compared to secondary and primary. Now, what is post hoc? You have compared primary, secondary, and tertiary together as one. Now you want to see where this significant effect you've seen in an ANOVA, where is it strongest? Is it between primary and secondary? Is it between primary and tertiary? Or is it between secondary and tertiary? So you break your ANOVA into two groups. It will now turn it to like t-test. That's why you see when you run a post hoc, the result is a student t-test because the post hoc will do the mean age against primary and secondary, do the mean age against primary and tertiary, do the mean age against secondary and tertiary. You'll be able to tell between primary and tertiary, between primary and secondary, between secondary and tertiary, which two has a higher influence in the age. So that's what a post hoc does, because most times when you run an ANOVA, running 3 groups, 4 groups, 5 groups, you may not be able to tell exactly which two has the strongest influence on that outcome variable. So that is it. So the other one, which, yeah.
Does it mean that it kind of compares means of different categories?
Yeah. Yes, the post hoc breaks the 3 categories into 2 at a time.
Two. Okay.
Yeah, okay. So it behaves like t-test. So instead of looking at 3 categories, 4 categories at a time, it breaks it down into 2 so that you'll be able to tell which 2 has more influence. All right. Yes.
Okay.
So for the other one that has to do with the wrath, I didn't use any statistical process. This is an anatomical pathological study. So what we do is we slice the liver, you know, and test for the histopathology using microscope, you know, using lab. So it's not a statistical kind of, it's purely anatomical, like histopathology. So the microscope does the work. Okay. Then for the effect size, what the effect size really does is when you are in a situation where you didn't follow a systematic process in selecting your sample and in calculating your sample size. For example, you want to do a study and you just decided, oh, let me use 200. You didn't calculate any sample size. The fact that you are guesstimating your sample means that your tolerable error is already very high. Because if you had calculated your sample size, you would have accounted for a tolerable error of 5%. But because you didn't use any formula, you just guesstimated 200. So because your sample size was guesstimated, you run a risk of tolerable error, meaning that you may be using a lower sample for that study that is representative of the population. So they say, if you're going to do that, then increase the sample using an effect size, times it by 2, times it by 3, times it by 4. So if you guesstimate 100, using an effect size of 2 would be 100 times 2. So increasing that sample size reduces the error that would have come up because you didn't follow a systematic process in calculating that sample size.
Okay.
Thank you.
That's very important. Thank you so much. My last question is about the negative and positive.
I think you've asked, can we, so maybe you can come back later. Sorry, let's have other people.
Thank you so much.
Yeah, all right, thank you.
Yeah, thank you for that. So I'd like to ask some questions from the chat box. Would that be fine?
Sure.
Yeah, there is this one question by Simone who asked, what is the implication of design effect in cluster sampling?
What's the implication of what?
What is the implication of design effect in cluster sampling?
Oh, design effect in cluster sampling. Cluster sampling is one of the sampling that design effect is really accommodated. So design effect helps cluster sampling. Because in a cluster sampling, this is what you do. Let's say you have, maybe you want to do a study amongst public primary schools, and you have 100 public primary schools in your community. Now, you don't have the funds and the capacity to actually take sample from the 100 public schools. So what you do is, cluster sampling tells us that each of the public primary school is a cluster. So 100 public primary school in that local government means 100 clusters of public primary school. So you make a decision. That's where the design effect comes in. You make a decision. You just guesstimate and say, oh, if I use 2 schools, I will be able to meet my sample size. But before you do this, you would have calculated your sample, you would have calculated your sample size. But you have to guesstimate the number of schools that will help you achieve that sample size you've calculated. So how you select the school, the number of schools you selected, that one is by guesstimate. Oh, let me use 4 schools. Oh, let me use 10 schools. That's cluster sampling. So you choose 4 schools, which is 4 clusters of the population. So in that case, you're encouraged to use the design effect times your sample by 2 to increase that number. So that, like they say, because there is a guesstimation here, the higher, the better. Because once you have a guesstimation, the tolerable error is there, So increasing that number helps to minimize any tolerable error that may have formed.
Shall we move to next question?
Yes, we can.
Okay. Someone has asked, what do they mean effect size? They want to know the definition of effect size with an example.
Well, I don't know if I can provide a definition, but I've created a scenario where you improve the population in terms of your sample size because you have to appreciate the fact that in research, we make some assumption which is not applicable in real life. Imagine you have 5,000 students in a school and you calculate a sample size of 200. And you want to tell me that the 200 sample is a representation of the 500. That's a huge gamble. But research allows it. As long as you calculated that sample size systematically using the different sample size formulas, then it's allowed. Then it's okay. You know? So when there are cases where you miss some of these steps, whatever number you're using is already biased. So you have to increase that number to minimize for any tolerable error that may have resulted based on the guesstimation of the number that you have chosen. I think that's, I don't know what other way to actually say that, So effect size, increasing the size, yeah. So it has you can do an effect size of 2, 3, depending on how many you want to times your sample size, yeah. Thank you.
Thank you. Somebody else has asked another question. When conducting a cross-sectional study, how do you use your principal component analysis to determine your sample size?
Well, we do not use principal components, component analysis, PCA to determine sample size, really. PCA has a process and a function, what it does. For cross-sectional study, you can use one of the first sample size determination formula I gave. That one can calculate sample size for you. What principal component analysis does is, let me give a very good example. In one of my research, I used a tool where I asked the participants some questions, like 10 questions or 15 questions or 20 questions. They will answer that questions for me, but what they didn't know is the 10 questions, the 20 questions I have asked them, I will sum it up to be able to tell whether they have noise-induced hearing loss or not. That's what the health hearing, test questionnaire does. It has some questions that you ask the participants, but they will be answering the questions freely, but they have no clue that at the end of the day, I'm going to sum up those questions, have a score, and I'll be able to tell whether they have mild, moderate, or severe hearing loss. So when you have those sort of tools, you expect all the questions to be able to answer whether the participant have noise-induced hearing loss or not. So you have to test those questions, all of them, using sometimes, you use the factorial analysis, you can use the principal component analysis. What that analysis does is it puts all those questions and generates a coefficient. It generates a number between 0 and 1, like a Pearson's correlational coefficient. So you have 20 questions, and each of those questions has a number between 0 and 1. Anything above 0.5 is high, anything below is low, meaning any of those questions that have a coefficient 0.7, 0.8, 0.9 tells you that that question has the probability of detecting whether that participant has noise-induced hearing loss or not. But when you begin to have coefficient like 0.3, 0.2, it tells you that you have to go back and look at that question. That question is poor in determining whether the participant has noise-induced hearing loss or not. So principal component analysis is a good tool to be able to assess all your questions to see whether they are able to answer the outcome. You know, so that is the purpose that I know of that, and that's what I use it for. But for sample size determination, I have not used it before, but I may read about it. You know, I may not know it all. Yeah. So thank you. Yes, Asta.
Thank you so much for that. We're almost at the end of the program. I would suggest that we take just one question more.
No, it's okay. We still have time. Oh, okay. It's 30 minutes. Oh, yeah. I remember. Yeah. Okay. Yes,
okay.
please.
Nelson has his hand raised since like very beginning, so I'd like to take a question from him, and we'll end it here.
Okay, thank you, Dr. Felix, for a wonderful presentation. It was really good, and we are happy that you are able to give us very good talk. So I have some questions. The first question is related to if we are dealing with secondary data that have been collected for another purpose, but we want to use those data for our study. Do we have to calculate the sample size in this situation or not? This is the first question.
That's for secondary, you mean secondary data?
Secondary data, yes. Example,
secondary
there's a database available, example of case of tuberculosis that are there.
Yeah.
So I want to use that database. Do I have to calculate in the protocol? Do I have to write, example, the sample size
okay,
for that or not? This is the first question.
Okay.
I don't know if I can go because it's not always that we have this opportunity to be with you.
Sure.
Okay. The second question, Professor, is about normality. I know that we have these tests like Shapiro-Wilks, but I know as well that we can use Instagram to see the behavior of normality. But sometimes I don't know what is the best, if going through Instagram or going to these tests. So I would like to hear from you, because sometimes in Instagram, I think that is normal. But when I do Shapiro-Wilks, it gives me a p-value above 0.5. So I don't know if you can advise us what we can take like the most important, because sometimes there's discrepancies.
So for me, it's easier to actually use the tool that will calculate a probability value, which will provide the most accurate result. Like, for example, you may do a comparative analysis. You're looking at this percentage, it is 50. You're looking at the other percentage, it is 40. In your head, you can say, wow, 50 is higher than 40. But when you run the test of significance, you find out that the p-value is not significant. But in your head, 50 is higher than 40. But the p-value does not show that 50 is significantly higher than 40. So that is the danger you may fall if you use just histogram. You may be looking at it visually and say, oh, this is normally distributed. But internally, the variability you're not seeing the variability is being accounted for in the histogram. The statistical software sees that. So I would recommend using the Shapiro-Wilk normality test. All right. Then for the sample size, it depends. If you are doing a study where you're going to publish that work from that secondary data, the publishers may not ask for the sample size calculation. But if it's an academic work, like a PhD, master's, and the rest, trust me, your supervisors will want to know the minimum, because the sample size determination is the minimum sample. So if you have a database that is like 500, they would want to know what's the minimum sample so that we know whether that minimum sample is below or above the number of the database. That's why you need to calculate the sample size, not necessarily because you are going to adjust the database. No. If you have a database and you have a sample of 500, you're going to use the 500. If you calculate your minimum sample and you have 200, it doesn't mean you're going to now use 200. No, you use the 500. But it already gives us a clue that you are not going below your minimum sample, meaning your tolerable error is, you know, is good because your sample is higher than your minimum sample.
Okay.
Thank you. So thank you very much.
Thank you. Thank you,
thank you
Professor.
too. I know some of us may feel somehow we're not able to ask our questions, but it's good to work with time. But I promise you that I'm going to discuss with the AuthorAID and see if we can just have a session where we just do Q&A.
Thank you.
Yeah. So, and I hope that you would still join when you see the invitation, because it's actually for you that I've listened to the presentation. So it's easy. So you can note those questions down and we will see whether we will just have a session just for Q&A, and so that we will give opportunity for you to answer your questions. So if you have dropped your questions in the chat box, please write it down so that, you know, we will take it up on that day. Thank you very much. Yeah.
Thank you. Thank you.
Yeah. Over to
really
you,
wonderful.
Asta. Yeah.
Yeah, thank you so much, everyone, for joining. And thank you so much, Dr. Felix, for very nice session. We can see that from the number of hands raised and the questions raised. We are so sorry that we couldn't take all the questions, but you can get back to us regarding the questions and maybe we can discuss it there. I would like to request everybody to turn on their camera so that I can take a good picture to post on the social media. Yeah, if it is all right with you, please turn on your video. And a lot of us were asking about recording and the resources of the webinar. We'll get back to you soon with those. You'll be receiving it from the same email where you received the invitation.
Okay, and I also wanted to add this. I know someone posted something on the chat box with regards to principal component analysis in the aspect of reduction. Yes, we can use principal component analysis for reduction too. Reduction in the sense that, like you have, it's almost the same thing that I just explained. Sorry, I have to clarify this. It's also almost the same thing that I had explained. You have 20 questions. And at the end of the day, you want those 20 questions to be able to give you one answer, whether that participant have noise-induced hearing loss or not. That's a reduction process, all right? But you can also use it to actually tell which question does a better job than the other. So I needed to make that clarification that you can use it for both purposes. Thank you.
Thank you.
Thank you so much. Yeah, let's take a picture. Please smile or do some crazy poses if you want to. I will be taking take reference from Andy.
Thank you.
Okay. Okay. Thank you so much. I have taken a picture, and sorry that we couldn't take all of your question, but there is always other opportunity to learn at AuthorAID. We're also planning of having a tea time with AuthorAID on the 31st. So please check out our social media channels for that. We'll be releasing the registration link pretty soon. And if you want to stay connected with us on various social media, I have shared the link. I will share it once again. We're very active on social media and we share most of our resources and opportunities to connect there. So here are the links. So I have shared something about our community group, which is the Google group of more than 15,000 scholars. And we have very intense, informal, formal discussions going on there, and it might interest you. We also have Twitter where we are very, very active. We have Facebook account, LinkedIn account, And another interesting thing is you can contribute the resources for other community members at AuthorAID so that our scholars in different settings of the world can benefit from that. So if you want to do that, you can just click on the link there, share there, and submit the resources. And you can also contribute your opinions, ideas, experiences regarding your journey or something that interests you. So you can contribute the blogs and articles. So there is also the link there. So feel free to stay connected with us. Yeah, thank you. And lastly, I'd like to thank everybody for joining and Dr. Felix for hosting an amazing webinar. It was fun learning from you. Thank you.
Thank you, Asta. Thank you, Andy, for hosting me. Final words from Andy. Andy, are you not saying anything?
Andy, please talk, Andy.
I don't know how I can follow something as fantastic as that. Thank you for coming, everybody. I've never seen so many questions, so much of a queue of people with questions to ask. So thanks very much, Felix, for being on hand. And sorry that we couldn't take all of the questions that you've got. So thanks very much, everyone, for coming. And hopefully we'll see you soon on AuthorAID to kind of cover any outstanding questions that you've got. Have a good day.
Thank you.
You too.
Bye.
Have a good day. Bye-bye.
Bye.
Bye, everyone.
Bye.
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 Bye.